ME350 Example Problem for Convection Boundary Condition. For conduction through a plane wall in contact with the fluid as shown, develop the boundary condition at x equals L as a function of the geometry, thermal conductivity of the wall, convection coefficient, and external fluid temperature. Note that the control volume we will use for our analysis is indicated on the figure on this slide. Our first assumption for this problem is negligible radiation. This is a reasonable assumption for an opaque wall and for lower temperatures combined with strong convection. Our second assumption for this problem is one-dimensional conduction in the x direction. One example for when this is a reasonable assumption is for a plane wall in the central region away from the edges, where the thickness of the wall is small compared to the width and the height. Thus, the temperature will only change in the x direction and be the same at all y and z locations. Near the edges of the wall, the temperature will be likely to be three-dimensional, thus it will change in the x, y, and z directions. To develop the boundary condition at x equals L, we begin by applying an energy balance to an infinitely thin control volume at the surface, where the rate of energy entering into the control volume minus the rate of energy exiting out of the control volume plus any energy generated in the control volume must equal the rate of change of energy stored within the control volume. Because the control volume is infinitely thin, it has negligible volume. Thus, there can be no energy generated or stored within the volume. This results in a much simpler energy balance where the rate of energy into and out of the control volume must always be equal. Substituting in for heat transfer by conduction only on the left for an opaque solid wall, and for heat transfer by convection and radiation on the right for the fluid, we get the following equation. For this equation, the heat transfer rate is given per unit area, thus as a heat flux, which is indicated by the double prime, where the corresponding area is normal to the x direction. Next, assuming negligible radiation, our energy balance reduces to the conduction through the wall at the control volume boundary on the left equals the convection to the fluid for the control volume boundary on the right. Next, we substitute in Fourier's law, which is the rate equation for conduction, for one-dimensional heat transfer by assumption 2 on the left side, and we substitute in Newton's law of cooling, which is the rate equation for convection, on the right to get our final result. Again, this equation can be used to impose a convection boundary condition where K, H, and T infinity are specified. In the limit where the convection coefficient is 0, which corresponds to an adiabatic or very well insulated boundary condition, the temperature gradient is 0 as expected. In the limit where the convection coefficient is very high, corresponding to very strong convection, the surface temperature at x equals L will be the same as the fluid temperature T infinity as expected.